Okay, we're going to move into the section where we're talking about probes, and in particular, we're going to kind of group two types of probes together to speak about them in their generalities and kind of all the different sections and parts that are in these transducers to arm you with the information to talk about these and perhaps kind of understanding where you might be able to induce some of the failures that are more intermittent on the machines that you're working on in the field. And so the two types of transducers we're going to be kind of groups of transducers we're going to be talking about is standard probes. Those are really your more routine and traditional, the curve, the linear, non-imaging, those kinds of probes versus a specialty T-probe that we're actually calling out as a little different subset because there's just so many more parts to them that make that probe function. So here we're going to start off with a standard transducer. We have a curved probe and we have all these numbers here. And these are calling out specific parts of the transducer that you're going to be working with. And we're going to dive into each one of these sections. Okay, and here we're going to talk about section number 1. This is the lens of a transducer. So you can see number 1 here, and this is the gray area that I'm circling here. And this is really that they call the lens. This is the rubber that is in between the crystal and in between the patient that's being scanned. This is often a rubber compound and it helps transmit the sound waves. So as we spoke about before, sound does not travel through really hard and dense and rigid materials, but when it comes to rubbers and water and all these different types of mediums that transmit sound really well, that's what helps promote a great image and gives you all the information that you need for a diagnosis. So really critical here to look up the lens when you're doing a PM, making sure there's no cuts, no nicks, that it's properly sealed around the edges to protect the patient from perhaps some electrical shock. So really critical part as far as patient safety is concerned, really the most critical part because that's really the only piece that's touching the patient. Now, number 2 is the housing, and we're just talking about the body of the transducer. So the plastics that really have the purpose of the sonographer can hold the transducer there. It is sealed around the lens and around all the crystal and the circuitry and the PCB that's inside that really puts that crystal together, that whole assembly. And so check for this, check the where there's adhesives and seals to make sure there's no gaps, and if there's any gaps that can be easily be repaired. But this serves really two purposes. It protects the electronics on the inside, seals the electronics from the patient, a little less critical than the lens, but it also is where a user will be holding the transducer to scan a patient. Now we're going to move on to the housing strain relief, the cable, and then the connector strain relief. So all of these kind of compose of what a cable is, but we decided to break it out because these are very important different sections, especially for troubleshooting. And so let's just talk about them really quick. Number 3 is your housing strain relief. And so when we're looking at this, I'm circling around number 3. This is exactly what it is. It's a strain relief. It's relieving the strain. And so if you have a transducer like this, it prevents the cable from overfolding, especially when in use, to protect the wires on the inside of that cable that eventually go to the crystal and goes all the way down to the connector. And to appreciate how fine these wires are, I have a bit of an example here to where you can see these wires, and this particular case, they go down to 42 gauge. And now I'm going to put one in front of you here just to show this is actually a coaxial wire. So what that means is that there's actually a center conductor, insulation, ground, and insulation around that. So it's actually 4 different layers on this single wire, and the center conductor is actually finer than human hair. Well, we have the technology to repair all of that for you, but I want to share, how important that is, because if you overstrain these wires, and there's probably at least 128, if not more, in this entire cable, going from the crystal all the way through the probe to the connector, all the way through the cable. So a lot of fine electronics, a lot of fine wires, all very repairable, but this is exactly what it's doing, is it's protecting those electronics on the inside. And now we're going to move to the cable, which is number 4, and that's just really everything in between the strain relief up here and the strain relief on the connector. So everything in between. And I'm going to circle that for you here, so kind of everything in between over here. And again, it's just really, insulation around all and protecting all these cables to prevent damage. Again, look at that when you're looking at probes. You might see some track marks of casters running over the cable, because the cables do hang down, touch the floor, moving that machine around. Very easy to accidentally run over the cable. And again, you have a several 100-pound cable machine running over these kinds of wires on the inside. Just physics takes place. That's just a lot of force on a really small component there. And then at the end, we have a connector strain relief on here. You're going to see this section above here, and really, connector will plug into the machine. This is the connector strain relief, and when you're testing probes, you might be able to move this around. Very rare, but sometimes you might be able to induce noise from some intermittent broken wires here. Maybe shaking the connector around might induce some noise as well while you're there. But then again, this is preventing the cable from overfolding right from this rigid area here, much like the strain relief on the housing. Here we really have a connector of a transducer. We're not talking wireless. We're talking standard transducers, and that are used on really premium ultrasound machines, and they have connectors. And this connector we've actually broken out to be a connector housing, which is what's also called a can. This is just the external, could be plastic, could be metal, that is really housing all the electronics, the locking mechanism that locks it into the transducer if it's available, all the electronics and all these filter cards and inductors, multiplexers can also be inside these PCBs in here, but also is housing all the electronics for the interconnect to the ultrasound system. And so now, moving on to the connectors and pins, they're in here, and there's many different kinds of pins out there for different kinds of transducers, a variety of interconnects, but really important if those connector pins aren't securely locked to the ultrasound system. That can cause some noise, because they might be, doing this little maneuver where, you move it around a little bit and it opens, where it should be a closed circuit, and then it kind of comes back together, and you'll see, some noise coming up on the image. So something to keep track of there. Keep those clean if you can. No fluids for, in this area when decontaminating transducers. Avoid that at all costs. But do keep these pins clean, some isopropyl alcohol if there's any issue there. Keep dust bunnies out of there. We've seen dust bunnies cause shorts across these pins, which cause some pretty severe damage. But in just talking about this part of the transducer, typically pretty robust. We don't see too much damage down here. Typically more on the crystal and line side towards the front of the transducer. So now we're going to move on to T-probes. There's a lot more components on a T-probe than a standard ultrasound transducer. However, many of the parts have the same application and function as they do in a standard probe, but there's some other extra hardware and electronics and features that make this probe really special. But this probe is designed to go down the esophagus of a patient and, again, to go scan the heart with the clearest image possible with no bone density in the way to interrupt an image. So an extraordinarily powerful imaging tool that is extraordinarily popular. And if your facility has these, they just live in a caustic environment. They're in the esophagus, in stomach acid, so acidic chemical there. They're around a lot of surgical equipment, so prone to getting stabbed and cut and all these things that could expose the internal electronics. That's bad for patient, number one, but also bad for the electronics, number two. And on top of that, when they're getting decontaminated, they're sitting in caustic acid again to decontaminate. So and then they get washed, by whatever technician is taking care of that at your facility. They're literally getting washed. So water and electronics, they don't mix, and the electronics always loses that battle. So really pay attention to how these are being cared for, transported, and used, and really critical to really inspect these transducers after every study to see if there's any potential damage, and if you can catch it early, can result in a relatively small repair cost relative to a full replacement of this specialized device. All right, we're going to start on the tip of the probe, the most sensitive area of the probe. It contains the crystal and is really what is doing the heavy lifting to send and receive sound to get an image of the heart. And so at number one, we're going to talk about the head and distal tip. And on the T probe here, that is this section. That is a section that is the plastic or urethane or whatever material is being used, enclosure that contains the crystal and all the flex circuits and the electronics that are connecting the crystal to the other end of the probe and the connector. This is the most sensitive part of the probe, and unfortunately, just by design, it suffers the most damage because it swings around so easily. So if you actually have the handle here and you move the handle, well, the distal tip moves as well, but it moves at a far higher speed because it's whipping around and causes can take a lot of damage. What we think is a small movement on the handle side, it just swings that tip and it can hit the side of a door, side of a machine, operating table, the floor, whatever have you. Really fine electronics in here, resulting in that kind of impact. It's a really sensitive area that you want to take care of in every single phase of the life cycle of this transducer. Now, the lens on this particular probe, you're going to see these on your Epic systems, is that square right there. And that is the lens. It is on top of this matrix, crystal here, a really sophisticated technology. And that lens is again a rubber compound of sorts that allows the crystal to send and receive sound through it. And then the bending section is right below it, and so it's from the bottom of the distal tip to the top of the insertion tube here, and this allows the transducer to move. And so if you have your heart is here, that allows the physician to manipulate it inside your esophagus to get right next to the heart to get a great image. So is that vulnerable to damage? Absolutely, and so is the lens, especially to some lacerations of surgical equipment, some accidental bites from a patient. Anything kind of jagged, anything kind of sharp can lacerate or put a micropuncture in these areas. And so what you want to do is inspect all of this every time after every study to see if there's any damage. Again, if you can catch the damage early, that could be really a phenomenal cost savings strategy, is to get it repaired early to avoid that costly replacement, because corrosion sets in, and at that point there's just nothing to work with on a repair. Okay, we got the insertion tube here. And it's really, I'm going to draw and trace the insertion tube for you, and it stops right here. And this insertion tube is a flexible tube that all of you are probably very familiar with. It's on endoscopes as well, but the insertion tube is the tube of the T-probe that allows the T-probe to have the length and flexibility to go down the esophagus to get an image of a patient. So things to watch out for on here is that it houses all of the mechanical lines that allow this transducer to move. And it also contains all of the electronic signal lines that we talked about here, from the crystal to the connector. So it moves. And so when things move, it's going to chafe over time on the inside. So what we recommend is storing these as straight as possible when not in use. A lot of facilities actually hang the handle and let the probe hang straight to reduce the amount of tension this probe endures over its lifetime to protect those internals. So the insertion tube, the common failure here is not common. If it does, typically it's the numbers that you have, the markers that denote depth for a user starts to fade a little bit. But as far as durability to bites and all that, is actually quite durable. It would actually get crushed there's a metal coil on the inside that gives the structure of the insertion tube, and it's more common that this will get crushed and crimped. We'll talk about later, but the crushing and crimping won't puncture the insertion tube, but it will go from a circle, and then it'll get crimped down to be a oval, and now all these wires and articulation lines and all that are kind of operating in kind of a weird area that it's not supposed to, and those can start to rub together a little bit. So something to watch out for, but not a common failure. So here we're going to talk about the middle part of the probe, and it's really the transducer controls and the strain relief. The controls are really the knob here, and this controls left to right, fore and aft, and then you can lock it with this lock here. And pretty simple. It's just moving the distal tip around, and then the strain relief here. So you now have the strain relief on both sides of a transducer here. On the handle, strain relief here, and the strain relief here. And again, these are strain reliefs that we've talked about before, just trying to protect the overflexing in these really critical spots that can actually get a wire to fold, and if it folds and it cracks, then you start getting noise in your image because of that intermittent connection. So this is going to look familiar for any probe. T-probe's no different. We got the connector strain relief. I'm going to circle that for you here. Same thing as a standard probe, protects from overflexing. The connector housing, this is just the housing, metal or plastic, that contains all the electronics on the other end of the probe that connects to the ultrasound machine. And then the cable. So the cable here is simply the cable that goes from, really in this particular case, the handle of the T-probe down to the connector that also houses all of these circuits, and that go from the connector all up to the crystal and back. So moving to some parts that are really specific to a T-probe, you have your control housing handle, and that's really this part here, and this houses a lot of the controls, all those wires we were talking about here, uh, run through this, and then now we have these control knobs that are controlling the distal tip. All the mechanicals are inside of here. Careful, don't put this in water. If you're gonna wipe it down, but we've seen this actually get dunked in water and sit there, and water will infiltrate it. There's some O-rings in here to protect, kind of some light moisture from getting inside here, but it's not meant to be underwater for any period of time. And so we see a lot of corrosion that occurs in here where, it might slip into a sink, and then, things in here start to corrode, and it's corrosion's tough because, you can clean it at its early stages and there's no harm, no foul, no damage. But if it sits there for a while, it literally eats away at the metals and starts pitting it and starts, really, eroding at the material to where there's just nothing else there. So it's something to look out for. And then the control housing, strain relief, kind of touched on this before, but there's a black strain relief here. And this is something that it doesn't fail often, nothing too much to worry about, but just preventing the overflexing of all the articulation cables and all the fine microcoaxial lines on the inside of the insertion tube.